All right, I think we can start. So, hi everyone, thank you for joining us today. Welcome to AryaXAI's webinar Beyond Explainability Evaluating XAI Methods with Confidence using XAI Evals. We're excited to have a diverse and enthusiastic audience with us from data scientists, ML engineers, tech leads, and decision makers, and all coming together to explore a vital component of building trustworthy AI, which is explainability. I'm Sugun and I'll be your host for today's session. Here's a quick look at the agenda. We'll begin with a short introduction to AryaXAI, who we are and why this space matters to us. And that will be followed by a deep dive into XAI Evals library and also the latest open source framework to evaluate post-hoc explanation methods across models and modalities. We'll further walk through some of the key explainability techniques and evaluation metrics supported by the framework. And this will be followed by a live demo showcasing how you can use XAI evals to generate and assess explanations for both tabular and image data. And finally, we'll open up the floor for a Q&A session where we'll take your questions. So throughout the session, feel free to drop your questions into the chat box below, or you can use the Q&A tab and we'll address them towards the end. So let's dive right in. To take us through this work, we are joined today by someone deeply involved in building the tools we're discussing. It's my pleasure to welcome Pratinav, a research scientist at AryaXAI and the lead author behind the XAI Evals framework. So he's been at the forefront of AryaXAI's mission to create actionable, accessible, and reliable interpretability tools for machine learning practitioners. So without further ado, let's get started. Over to you, Pratinav.
Yeah, thanks a lot for that. Hi, I'm Pratinav, and let's get started. First about AryaXAI Alignment Labs. So, right now we have labs in Mumbai, Paris, and London. So, our goal is again to solve interpretability, alignment, AI safety, and risk. And how do we plan to do so? Is like building new techniques, working on open source tools, collaborating with academic and other labs, and few other tools which we have publicly released right now is DL-Backtrace and XAI Evals. So today we'll be talking about XAI Evals and why is that evaluation of explainability is really important. And we are also hiring for a lot of roles right now. So in case you're interested, feel free to reach out. So coming to the main point, like in today's world, like again, the big problem is we have a lot of mission critical tasks where AI is applied in order to improve efficiency. But like as you can see, you have healthcare, pharma, banking, insurance, like across the domains. Right now, you have like governments as well as regulators who are also using AI and are very, I would say, um, concerned about AI and its use cases. The reason being, like again, creating models is easy, but making them acceptable is hard. Why am I saying this is like you can just create any deep learning model or use any model from let's say Hugging Face. However, you're not sure like how the model is trained. You don't have any idea about the ways in which the model makes a decision, like with especially in these particular fields where it is highly regulated. There's a very specific regulatory compliance on AI use, and because of its untraceability of decision making and uncertainty, it creates a very, I would say, important problem in today's world. And with just let's say we can create a model in let's say next 1.5 hour for a particular use case. However, making it acceptable from all stakeholders is something which is I would say really hard. Like you have your product team, you have your risk team, you have your audit and regulation division, and you have your customers. So how do you ensure that you have confidence from all these different stakeholders while you are actually creating your AI models? So one way to go about is again, you have explainability. However, how do you ensure like your explainability is actually correct? Like sometimes you can say wrong explainability is equally bad as no explainability because with a wrong explanation method, you can actually fool your stakeholders and this will create a distrust between all of those involved. And hence they won't actually have a trust in the machine learning or AI use case or uses itself. So what is like, as I mentioned in the start, you have government regulators who are actually really interested in solving this and are really concerned about this problem. So what exactly is like different, I would say, governments are doing. So in Europe, you have EU AI rules which are coming up. They have a lot of things around model risk management, explainability, and use of AI. In US as well, you have different rules coming up. In other countries, in such as UK, in India, you have different set of rules which are being introduced by these stakeholders and regulators. So again, for someone who is new to the field, why there is this problem with AI? Like people have been using machine learning for, I would say, last decade, and this wasn't much of an issue. So why this problem with AI specifically? The reason being, like you have deep learning models which perform really good but are opaque, and we actually don't know how they make decisions because you have a series of, I would say, mathematical operations being performed, and to make it transparent, it's really hard. You have different methods to explain such models. You have model agnostic methods, which are basically in, I would say, you can call it as surrogate modeling, which is their Lime and SHAP are two traditional and very used examples. However, they are often costly and very sensitive to data changes. You have gradient-based methods, which are based on, again, the gradients of the model. However, again, it very much depends on the baseline and it's complex to interpret. And there is a lack of unified metrics. Like you have all these methods, how do you compare which method is good is something which is a bit problematic. Okay, so again, coming back to the black box problem, which we have right now in AI, like with the increase in, I would say, uh, let's say the compute is, I would say, not a very good idea, but the increased number of parameters, we are unable to understand the models which we are using. Like we are very happy with the performance, but what about understanding the models which are actually making decisions? So again, it's similar to the previous slide. So again, like coming to the main topic of today's webinar is, again, how do, like, you have interpretability, you have different methods through which you can understand interpretability, like in as, and also in today's world, which you have having large deep learning models, which are billions of parameters. You cannot be just using gradients and be like, okay, this is how this is working. You need something which is much more concise. You need something which can be understood by different stakeholders and can be applied to high stake applications. So with this, explainability becomes really important because, again, like you need this explainability and interpretability in today's world. You still have black box models which are coming up with no solution around how to explain these models. And again, there is explainability work being done, but how to scale it is something which is very difficult. So for someone who's very new to explainability, you have something called global explainability, which provides like a comprehensive overview. You have local explainability, which just focuses on individual predictions made by a model. And most of these methods are post-hoc in nature. By post-hoc, what I mean is when you have trained a deep learning model, and then you're trying to create this explainability when it's trying to, let's say, make a prediction on a particular data. So that is what post-hoc explainability is. And right now, you have a lot of post-hoc explainability methods which people have been using for the last decade. You have Lime and SHAP, as I discussed before. You have GradCAM and integrated gradients, which are gradient-based. And you have DL-Backtrace, which is again a model agnostic method, which we have worked on. And it determinately assigns relevant scores without any baselines, and it's much more stable. So again, what's the problem then with, like, you have all these methods? Why cannot we just decide, okay, this one is good, this one is second, this one is third? So first thing is, for explainability, you don't have any ground truth. You don't know, okay, if the explainability method which you're using can actually be compared to a ground truth and you can then rank. So this creates another problem. So how do we then again quantify which one is good? So you have different metrics which are again based on perturbation. You have different ways to quantify, okay, which method is good. However, in terms of evaluation itself, there is no universal conscious, like how exactly should we evaluate explanation methods? They're very much subjective. You can go to different domains, different researchers are using different ways, and they can be easily fooled. That is another problem. And again, like comparing them across different fields are, I would say it's a big problem. So again, like what can be done? Like one way is to, like, how can we standardize it is, like if we are able to standardize it, it creates a uniform benchmark for, I would say, different sectors to follow. And And we need something which is much more robust, okay, which cannot be easily fooled. So with keeping all this in mind, we came up with XAI Evals, which addresses the challenge of black box model. You can have any black box model, let's say using neural networks, using CNNs. So we are particularly targeting tabular and image data. And it takes into account the importance of interpretability. You can have any interpretability method which you have. And it supports a lot of post-hoc methods. So we're introducing XAI Evals as a Python package. So it is open source in nature. You can try it out for any of your tabular and image data. And as it has integrated various methods, as I mentioned, you have SHAP, LIME, GradCAM, DL-Backtrace, and more. And it supports a lot of different metrics, which like faithfulness, sensitivity, robustness, which are commonly used in the evaluation space for explainability. And by using this, one is able to enhance interpretability and trust. Um, and how is that? So I'll talk in the next slides. But overall, you can use XAI evals again with a large number of models across both normal machine learning models, deep learning models from PyTorch and TensorFlow. You can generate your explanations in a very structured format, which in turn you can use for different use cases in your production pipeline. Then you have different evaluation metrics through which you can decide, okay, which explanation method is good. And then again, you have benchmarking. So yeah. Uh, so with all this in mind, like why is evaluation really important is one question which might come to your mind. The reason being, okay, you have all these methods, you are working with a regulator, you are saying, okay, our model is explainable and it doesn't contain any bias. So when you're saying, okay, you have chosen certain methods, how do you put it towards the regulator? Because again, you have all these methods, but you don't have is something like a quantifiable way. So this is where XAI evals come to the picture. And especially with methods like SHAP and LIME, which can be easily fooled, this is something which can really help in your, I would say, deployment of your model and real world cases. So when we're evaluating explanations, we have like certain areas. One is faithfulness, which is really important. Like how well your actual explanations align with the model output. Let's say some region is really important based on explainability. So in turn, it should also, if we perturb that region or we change that region, so your prediction should also change. So faithfulness is one area which is really important. Another thing is sensitivity. Like can we, by introducing, let's say, some random noise or some data change, can we just change the attributions by a lot? That is one another area. The another thing is comprehensiveness, like how much the output drops when we are improving the features. Like let's say in terms of model confidence, how does the model confidence drops when we are removing important features? And lastly, the sufficiency of these important features, like whether most important features alone are again useful for explaining the model, or is that not the case? So if that's not the case, your method may not be really good. So we have all these metrics. We have faithfulness-based metrics. We have sensitivity. We have comprehensive insufficiency. We have monotonicity, and we have sparseness. So sparseness is something which a lot of people use, but it's highly debatable. So based on the explanation method which you are using, uh, it's something you will have to decide whether you want sparse explanations or whether you want explanations which are much more descriptive in nature. So with this, I come to the library design. So you can just pip install our library. So pip install XAI Evals. In this, we are right now supporting two data types, that is tabular and image, with support of text and furthermore modalities coming soon. In tabular, you can again work with machine learning models as well, because again, they're largely used in the industry as well. So with machine learning models, you can have SHAP and LIME again, because they are surrogate based methods. And through that, you can try and test, okay, which method suits the best. Similarly, for deep learning models, you can have both models in PyTorch and TensorFlow. And in that as well, you can have SHAP, LIME, TensorFlow explanation, Torch explanation, as well as integration of our in-house DL-Backtrace. For image, again, you have PyTorch and TensorFlow, where you can use PyTorch Explainer, TensorFlow Explainer, and DL-Backtrace Explainer. So that's the overall library structure. And these are all the functions. Again, it's same as what was described in design diagram. So with this, again, it's the same thing. You can train your model. You can have utilized an XAI Evals to generate explanations if you want to see specific predictions. And after that, you can use the same XAI Evals library to evaluate the generated explanation methods. Okay, so by generating on a small subset, and then you can benchmark and compare. So with this, I'll be moving on to the demo part. Just give me a second. Okay, so 1 second. Yeah, so this is in Lightning. We have a Lightning Studio setup with everything in the environment being set it up. So you can either use this, or we also have collab notebooks with the library. So you can use that as well. So we'll be starting off with 3 examples. We have first is again, as I discussed again before, you have ML models. Then we'll be showing ML models on tabular data. Then we'll be showing deep learning models on tabular data, and lastly will be images on CNNs. So that's how we'll be moving forward. So this is the first use case. In the meanwhile, while the studio is getting ready, I can just scroll you through. So again, you import all your explainer methods. So we'll be using SHAP and Lime in this use case. Then you have for metrics explanation methods tabular. And for model, we are using a random forest model. And data set, we are using an iris data set. So let's get started. So in this, so we have already downloaded the library. You can do the same over Collab notebooks, which we have in our GitHub repo. Then we are just training a small random forest classifier for the data set. And after that, we are using SHAP. So this is how we have a SHAP explainer. So similar to like what happens in production is, again, you need a very specific format when you're using something like this. So what we have done is we have created those data structured explanation methods. So with similar to your data set instance, we'll add another column of attribution where you can see the attribution values in case you want to do something more with the attribution values. Similarly for Lime, again, we are doing the same thing. So everything is fitted on the whole training set for both Lime and SHAP. And after that, what we do is we try to compute all these different metrics for Lime and SHAP. So this is for Lime first. So as you can see, it barely takes, I would say, a few seconds. So we are computing all the different metrics which we discussed earlier. So we have faithfulness, you have infidelity, sensitivity, comprehensiveness, and more. Whereas this will repeat the same process for SHAP. For SHAP, it takes a bit of time. So 1 second. So yeah, this is the metrics for SHAP. And let's now compare it. So as you can see, like with both the things, the faithfulness is negative, whereas if we take the value, what we see SHAP is much more faithful. Whereas for infidelity, it is having a little bit lower infidelity. Hence, we can say, okay, SHAP is a much more better method as it can have like a better goal orientation with much more model aligned explanation. Whereas Lime, although it has higher sensitivity and monotonicity, it is ideal for situations where there is subtle changes in the input features. Okay, so both the methods have their own positives and negatives, but it's dependent upon the use case you're using. So based on the industry and the data type, you can choose, okay, which method does suit my own purpose. And based on that, you can use that in order to comply with the regulators. So that is one instance for tabular data and machine learning models. The next, we'll be moving on to tabular data with deep learning models. So for since we are short on time, we'll be using a very small model. And so we are using the Lending Club dataset, which is a very specific, I would say, a baseline for fraud. And like the model which we'll be using is a small MLP model. So it has around 3 layers and a few activation functions. So let's just start running it from scratch. Okay. So I've already done the pre-processing so that we can just directly use it. And yeah, so as you can see, this is the particular model which we'll be using. And it will take a bit of time to train. So if you want, we can let it train for a bit. Yeah, almost done. Yeah, so after that, let's test the model and see how things are fine. Okay. So if you see the model is decent, you have 0.88 F1 score. So that's a good score. So we can say, okay, our model is good. Now we can see in a similar way to your machine learning models. You can explain your tabular models with, let's say, this is using saliency, which is essentially gradient. So for each feature, you're actually able to see the value as well as the attribution. Similarly, for this method, which is integrated gradients, which is again gradient-based method, you can able to see all the attribution values. This is for gradient SHAP, a variant of SHAP. So it's deep lift. So with deep learning models, what we have is a lot of different variations for explainability we can use. We are also able to use DL-Backtrace, which is our in-house method and should be much more stable. So now we'll be computing the metrics part. So this is, let's say we are using deep lift, and in a similar way, then we are using integrated gradients and gradient SHAP and backtrace, okay, in two ways. So as we can see, like it didn't take that much time. And if you see the metrics, okay, DL backtrace in terms of faithfulness is much more stronger. Okay. So that's the case. Whereas if you see in terms of sensitivity and comprehensiveness, it's much better. You have other methods which have slightly better faithfulness and slightly higher infidelity, but they're still closely aligned to model behavior. It's very much dependent on the use case which you're using. Okay, so if you value much more on the sensitivity and comprehensiveness of your explanations, you can use DL backtrace. If you feel okay, you want slightly better faithfulness, then you can use integrated gradient. So again, it depends on the use case and the model type. Okay, so that's the second thing. On the third part, we'll be moving on to images. So with images, the thing is, again, since we have a very large model, it sometimes takes a bit more time in order to compute the metrics. So as you can see, we'll be using a quite big model. Okay, I would say quite big in a sense compared to, let's say, MLP, but it's still small. You have like a lot of convolution layers and batch normalization layers. And yeah, so let's say this is based on a dataset called CIFAR, which is a very standard computer vision dataset. So we train the model, we get an accuracy of around 0.899, which is decent. And then we take like a subset of the test set. So as you can see, you can have like original image like this. Then you have different explanation methods. Here you are using occlusion, which is a gradient-based methods. This is GradCAM. Then we are using again, DL-Backtrace. So in DL-Backtrace, again, as you can see, it's much more detailed. Next thing which we do is we work on the metrics part. So you again, similarly, you have a explanation metrics image where you can define the framework, and based on that, you can give your starting indices and ending indices as well as the metrics name on which you want the explain like the metrics to be computed as well as the XAI method name. Another thing is based on your model type, you can give like whether you want softmax true or not. So here we are getting okay faithfulness score to be minus 0.81, sensitivity to be this, and this is, we are just computing on one batch, so batch size 1. Similarly, we did it for GradCAM. Here, as you can see, the faithfulness score is in positive, which is a good sign. Max sensitivity is 0.23 and batch is again 1. Similarly, we did it with okay DL-Backtrace. So in DL-Backtrace, as you can see, you have all these matrices. And we also did it for DL-Backtrace in contrast mode. So we have in both things a positive value. And as you can see, okay, so with DL, what we can see is, okay, with backtrace, we're getting the much higher faithfulness correlation compared to GradCAM. And in terms of sensitivity, IG is the highest. But again, that's much more on the gradient part. So what we can see is DL-Backtrace has highest faithfulness, indicating it aligns well with the model process. Integrated gradient has lowest faithfulness, which indicates, okay, it's not very much good. But again, this is also dependent on the batch size. Right now, for the sake of time, we are just doing it on one batch size. But as you increase the batch size, things may change on the metrics part. So if you're doing it, let's say, for deployment purpose, it's best to do it on a holdout test set. GradCAM has a lower sensitivity, making it much more stable. So like again, in various cases, especially for computer vision, you focus more on faithfulness, whereas max sensitivity again can be one thing. So we have other metrics as well, which you can explore. Going with this, so we have like illustrated all three different use cases. In the meanwhile, let me show you the library as well. Give me a second. So this is a library. It's fully open sourced, as you can see. Um, as I mentioned, this is the overall library structure. So we have different explainers. We have mentioned everything. So you can try it out for yourself. This is the notebooks which I currently showed you. So you can have a look and run for yourself over the collab version. And you have all these different models which we are supporting for machine learning. We have almost all the models which are there in sklearn and people use in like in day to day for different tasks. Then you have different small code snippets which you can try it out. Let's say for SHAP, for Lime, for all basic classes. Then for deep learning, you have Torch Tabular Explainer, through which you have various different options through which you can try out explanation methods. Similarly, for TensorFlow, we have these methods. Backtrace, again, you have just two methods, default or contraster. Similarly, for image, you have another classes. So you have Torch Image Explainer, through which you can try out in Torch different methods. Right now, we showed for TensorFlow. Similarly, for TensorFlow, it's similar to the example we showed. And DL-Backtrace as well. You can similarly create the model and test it out for DL-Backtrace. So, and this is for the metrics calculation part. So you can create a different class for metrics evaluation. You can have your different, the explanation method which you want. And you can give the train and test set, and based on that, it will create the metrics part. So we have a lot of different metrics which you can choose for. So for tabular, we have faithfulness, infidelity, sensitivity, comprehensiveness, sufficiency, monotonicity, complexity, sparseness. These all cover like the major points which are there when you're trying to evaluate such methods. Similarly, reference values we have also given. So in case you're new to the field, you can actually make out, okay, what does these values actually indicate? In a similar way, we have also did it for image metrics. So in image, you have a lot more different metrics. So you have faithfulness correlation, max sensitivity, MPRT is widely used in the field, faithfulness estimates, as well as you have the reference value so that you can compute. We have a few more in our private version, so you can, that's also there in case you are interested. So yeah, like these all are the different methods which you can try out. And these are the libraries which we are using. So you can, we are acknowledging it as well. So yeah. So overall, this is how I would say DL-Backtrace works in terms of demo part. Like our key findings while working on XAI Evals is like, one is the field itself is very much divided on how to quantify explainability. Quantitative comparison makes it much more easier, I would say, to compare different explanation methods, highlight their strengths and weaknesses. And we can also identify reliable explanations. And it also enhances trust because you're now able to quantify things in a much more efficient manner and can help with different practitioners to select different methods and refine explainability methods so that it actually works well in terms of, I would say, qualitatively as well as quantitatively. In modern applications, I would say it enhances the understanding. It helps, especially in the regulatory industry, to find the best explanation method based on your industry and model. And hence, you can actually use the best method possible. It can also help in the fairness assessment, like you can assess the fairness of explanation method which you're using as well as your AI systems and mitigate any biases which you have. And especially with the regulatory compliance with the EU rules coming up where they want explainability, but there's still no specific guidelines. This is how you can actually adhere to different GDPR and EU AI Act, as well as ensure there is transparency in the AI operations of your organization. So in conclusion, what I would say is through XAI Evals, we're trying to address a very critical gap which is there in post-hoc local explanation methods, in which you have different explanation methods, but in most cases, people don't know they can be compared or you can actually evaluate them. In this, we are trying to provide a unified open source method through which you can compare different, I would say, different models for different tasks, as well as you have a quantitative method surrounding most of the matrices you would like to compare around, and it enhances the trust and transparency in your overall method. So alongside different AI evaluation methods, you also have the explanation evaluation methods through which you can select your best method. So right now in future, we are trying to support newer architectures like transformer models for NLP is, I would say NLP itself as a domain is something which we are working on. And with the upcoming, I would say in the last 2 years, the rise in which NLP applications have seen, NLP is something which is a bit hard, but actually really important to solve for explainability evaluation, especially in a black box manner. Alongside, we are also incorporating different evaluation metrics, different explanation methods for different, as you can see, for in some of the methods, we are supporting only a few methods. So we are trying to expand like to all the methods which we can, as well as different tasks. Graph neural network is again something which organizations are really interested in because they're really useful in things like fraud as well as in different aspects. So graph neural network is also something which we are looking into integrating. And we are also trying to make further improvements so that it can easily integrate to your existing ML pipelines and tools. Right now itself, you can integrate it with our open source tool, which we have. However, in order to make it much more accessible, we are trying to improve certain architecture choices which we have made. So yeah. So with this, I'll be concluding my talk. So I would request you can have a look over GitHub repository. We have like very easy to remember AryaXAI hash XAI Evals. That is something you can look into. Also, we have released a preprint, so you can, if you go to the GitHub repo, you will find the link. You can go through that, or you can type this in your website, web browser, and you can find the paper as well. So yeah.
Sure. Thank you so much, Pratinav. That was a very detailed and insightful session. We already are starting next session, our Q&A session. So if you have any questions, please feel free to drop them in the chat box below. Pratinav, we have one question for you. It says, have you made any attempts to combine all these methodologies to provide some aggregate explainability, or is there a huge amount of deviation in the spread of explanations from each methodology?
Okay, I think we have tried to actually quantify different directions. So we have different metrics for, let's say, each of your different, I would say, fields. Let's say faithfulness is one direction and explainability quantification. So you have different metrics for that. We are trying to quantify them all together, but that is a bit hard because you have different ways to compute. So I think it's really dependent on the business. So if you are valuing, let's say, faithfulness over sensitivity, so you can select that particular metric. But that is something I think we as well as the community needs to look into in future. If we can combine all these things together and give like a straightforward single metric. So yeah.
Okay, cool. We have another question from Daniel. It says, is there a timeline to support NLP models?
Okay, so with NLP models, I would say we have a timeline. I would say in near future we will be resuming. So right now we had a few experiences with tabular as well as image models. With NLP models, it is a bit hard in order because the field itself and the community is trying to get new methods. So I would say maybe by the end of this year is something we can look forward to, but maybe earlier as well. So yeah.
Sure. Another question we have is, can you explain how XAI Evals balances between faithfulness and robustness when evaluating explanation methods?
Yeah, sure. So in terms of like this can be one thing which we can say. So since we don't have I would say ground truth labels when we are comparing or evaluating explainability, uh, robustness and faithfulness is something which is I would say sometimes I would say used interchangeably in the field, but through XAI Evals, again, you can have an idea when you're computing faithfulness, okay, how robust is your model? Whereas in terms of robustness, you can try to do similar adversarial attacks and try to see if your model is robust enough. But I would say both of them are really related. And when you're trying to evaluate, let's say, explanation method, and then you're trying to say, okay, if your method is faithful enough or robust enough, sometimes it comes out to the very similar point, but we have different metrics through which you can actually quantify it in a separate manner. So yeah.
Okay, thank you. And we have another question. How do we quantitatively assess and select between CHAP or LIME given their individual trade-offs?
Okay, I would say with both Lime and SHAP, again, if you're using a machine learning model, you don't have much choice because you'll have to use a surrogate method. But with Lime and SHAP, again, it depends on the use case. So with both of them, the problem is they can be easily fooled with different adversarial attacks which are there. So again, if you have a, let's say, a use case where you just want very specific or less number of features, then you can use SHAP. Whereas if you are really interested in, let's say, something which is much more global, which is a problem with Lime. So if you want like a kind of a global explanation kind of a thing, then I think Lime is much more suitable. But you have problems with both of them, and hence the regulators aren't very keen on both of them, especially if when you're trying to deploy deep learning models. With machine learning, it's much more explainable because you can see the actual decision-making process. So it's much more better to use something like, let's say, DL-Backtrace instead of shifting to Lime or SHAP. So yeah.
Okay. And can we use the library with other XAI methods like SAEs?
Uh, I would say if you are able to generate your explanation, that is something we'll have to look into for the future. The reason being, okay, we tried that approach while building the library, but for easier use case of the end user, what we did is we integrated the explanation generation method inside itself instead of you giving an option to give your explanation and then compute it. But yeah, maybe in future that is something which we can explore. We'll have to make a design change, but yeah.
Sure. And to the audience, if you have any questions, we are still open to answering all of them. Please drop them in the Q&A or the webinar chat. Okay. Another one we have is some metrics like faithfulness and comprehensiveness can be data sensitive. So how does XAI Evals handle variability across the data sets?
Okay, I would say that is something more on, yeah. So I think that is very much like, again, all these metrics are really dependent on the data which you are giving, because based on the data, the model is making a prediction. And since, let's say, you're giving something like auto distribution data, in that case, what will happen is your explainability might get really disturbed because the model hasn't seen that, so the model is unable to focus, and hence the metrics, say faithfulness or comprehensiveness, can be really shaken. So in that case, like with XAI evals, like you are able to actually see, okay, there is a very high variation in terms of, let's say, a very particular batch. So in case, let's say, there is something like that happening, there is a NaN value or your values for that particular metrics goes out of hand. So we have some corrective measures. However, that is something which has to be seen by the end user. So in terms of, let's say, with shift in the data, these values can actually shoot up a bit. So this can also be helpful in some cases, but that is something which needs to be tested out more so.
Sure. Another one we have is how well does XAI Evals generalize across modalities such as tabular versus image versus soon text data?
Okay, so I think in terms of generalization, because the overall idea is the same. You have certain areas through which in which you want to, I would say, quantify your explainability, how good it is. Like one is like simple example is faithfulness. So faithfulness is consistent across text, tabular, as well as image. You want to know how well your model is, how faithful your model is, or how sensitive your model is. So we have developed, like, I would say the overall idea is the same. The only thing is we are changing the implementation a little bit to support different modalities, but you will be able to compare like different modal, like I would say across different modalities, how sensitive is your model, how faithful is your model to different metrics. So yeah.
Okay. And we have a couple more minutes before we conclude. If you have any questions, yeah, we have another one. How we do we quantitative analysis on the image part?
Sure. So I think I discussed this. Like the thing is, you have different metrics. So when you have different metrics, what happens? So let's say, let me give you an example of maybe faithfulness, or you have MPRT and other metrics as well. So one good idea is, let's say you have a model. Based on the model, you created a prediction and then you calculated explainability. And through that, you are able to know, okay, what are the certain pixels in which the model is most dependent. You remove that and then you try to compare, okay, what's the model confidence now? And in a similar way, you can basically black out the entire image based on how important pixels are. And hence, you will get a, let's say, kind of a graph kind of a thing, and hence you're able to actually compute, okay, this is the area under the curve, and hence you have a quantitative aspect to it. So let's say, hence you're getting a quantitative value, okay, this is the area under the curve, and hence from that you are able to compute a metric. So in a similar way, we have different metrics, one around faithfulness, and through this you can actually quantify different values, let's say around faithfulness, and then you can actually say, okay, which metric is best for, let's say, you have told image part. So for image part, this is the metric which is best, and this is the logic behind it. So yeah.
Sure. And another one we have is there a preference of metric basis on use case? Like for healthcare, it need to be more truthful versus in finance, it needs to be more robust. So hence use respective metrics.
Yeah, I think it's really depends on your use case as well as your, I would say, stakeholders. Okay, so what I mean by stakeholders and use cases, let's say, as you mentioned rightly in the question itself. So let's say in some use cases, you need the explanation methods to be really faithful because you might be using the explanation methods for, let's say, a double check over the references. Like in medical, let's say, um, you might use the explanation in order to double check with the doctor's diagnosis, or doctor might use the explanation to double confirm whether the decision made is actually correct or not. So in that case, you need the explanation methods to be really faithful. Robustness is again depends, like with finance, robustness can be one thing which is really important. So again, it depends on the use case you're using, and with different use case, I think you'll have to sit with the stakeholders, understand what exactly is important for the use, and then you can actually compare, like as I shared in our library as well, we have shared details of which metric is can be used for which particular use case or what each metric actually interprets. So based on that, you can decide and prioritize certain metrics based on your use case. So yeah.
Sure. Another one we have is some metrics like faithfulness or comprehensiveness. They can be data sensitive. So,
I think I answered that previously. So yeah.
yeah. Okay. So we have a few minutes more if anybody have questions. Okay, another one we have is what are the future plan for the library?
Okay, so I think as I mentioned, so in future, one thing is again NLP is something which we are trying to integrate soon, because again you have different ML models or like different NLP models being used every day in different applications. We have a lot of, I would say, applications coming up which are just using a basic NLP model and just wrapping over it. So with such applications in place and with more EU, let's say EU regulations is one thing, but you have with the regulations which are coming up, you actually need methods firstly to explain these NLP models, because explaining these models is firstly tough. And the second thing is how you can quantify the explanation of such models. So that is something which we'll be working on in the next few months by the end of this year. That is one thing. Second is how we can quantify explanation of models which are black box in nature. That is also something which is being done in the industry, but we are also looking at it. That is something also we think we can try to work on. Another thing is GNNs is also one area which is really interesting. I think some work has been done around GNNs in the academia, but GNNs is also one area we think will be working on next. But for the time being, I would say NLP is, and by NLP I mean text is one modality which we'll be looking on in the future. Text and maybe multimodal. So yeah.
Cool. Another one we have is how should teams interpret a high sufficiency score but low monotonicity in practice? And what does that say about the explanation quality?
Okay, so in terms of high sufficiency score but low monotonicity score, okay. Again, like the again, it's very much dependent on what particular use case you are doing. If you see, okay, like in your particular use case, sufficiency is fine, but monotonicity is something which is uh, a bit like not used that much. So it again depends on the use case on which you are using it. So yeah, like if it's something which is, let's say, um, let me give you an example. So let's say you have very high sufficiency score. What will happen is um, since you have a very high sufficiency score, like only a top K features alone will match the original prediction. Okay. So like basically model is just very much dependent on a very small subset of features. Maybe what you can do is like you can use that particular features to help the model score, like just use that particular features itself instead of using all those features. So in terms of model development, that can be one area. But if you are getting, let's say, low monotonicity scores, um, like again, that can indicate something in terms of how your ranking of different feature importances. So again, like it's very much dependent on the use case. So yeah.
Sure. I think we received some excellent questions today. And, that brings us to the end of today's webinar. Just thanking everybody once again for being with us. And we hope this session, offered valuable insights into, how XAI Evals can help us bring transparency, reliability, and auditability into modern AI systems. We'll be sharing the recording of the session with all the attendees soon. And if you like to, know more, explore more about AryaXAI, so do check out or connect with us on LinkedIn and check out our website as well. And we are always eager to build with the community. Thank you once again. Thank you, Pratinav. And we look forward to seeing you at the future sessions. Thank you so much.
Yeah, thanks a lot. And yeah.